Happy day students. Let us continue with electrostatics today. In the last class we studied about the charge. So today we are going to talk about what happens around the charge. As we discussed in one of the property that a charge at rest creates electric field around it. What does that mean? If suppose one charge is there and around it there is electric field because of that. Okay. And if another charge is coming towards it or it enters into electric field, so our own charge, the first charge, is going to apply a force on it. Okay, that we call as electrostatic force. Let me make it on the board and I'll try to explain it. If suppose we have a charge Q, okay, and its field maybe is up to this range, and you brought another charge Q in this one. So what will happen? This charge Q will be subjected to a force because of this charge. Okay. Which force? Electrostatic force. It's called electrostatic force. Okay, we are going to discuss about this now. Okay. Now, if suppose I take two charges, Q1 and Q2. There are two charges, Q1 and Q2. And the separation between them, let's say, is R. Okay. Now what we are going to do, we are going to make it fixed. Suppose I made it fixed and I am going to release it. What's going to happen? If I consider both are positive charges, okay, what will happen? If I am going to make it fixed, this will move. Either it will move in this direction or it will move in this direction. Okay, so since it's moving in opposite direction, we can say that the positive charges actually are going to repel each other. Positive charges repel each other. Okay. If suppose now I make this as fixed and that is free, so what will happen? That charge will go away. So we know that if this is positive, that's why this charge is going away. So two like charges are going to repel each other. Same thing we can do with the minus also. If I am going to take this as minus and here also minus, okay, make this fixed and see what is happening to that. So we know that that will also go away. Same way, if I am going to make this as fixed, and this is free. So what will happen to this? This will go in this direction. That means like charges are repelling each other. Like charges repel each other. Okay. Then what is next? Make this as positive and this as negative. Now let's see. Make it fixed. Then where it will go? It will go towards it. Okay. Then make this as fixed and see this will come towards. So we know that now unlike charges attract each other. This is the proof of that. Okay? Unlike charges attract each other. Again come back to the original one. Let's say the two are positive charges. Okay. Make one charge as fixed and other charge as free. So suppose Q1 is fixed. Okay, we made Q1 fixed and this is free. So by making it free, we can measure the force. We can measure the force applied by Q1 on Q2. How? We can connect it with the spring balance. And we can find out that with what force it is going to exert force on spring. And we can measure that force. Okay? So we can measure this force. Same way, we will make this as fixed. And measure the force on Q1 the same way. Then what we found? The force exerted by Q2 on Q1. Force exerted on 1 because of 2. And force experienced by 2 due to 1 is exactly equal in magnitude. Okay? Force experienced by 2 on 1 is exactly equal to the force experienced by 1 due to 2. Exactly equal. Okay? And in opposite direction also. They are positive, that's why the directions are like this. If this is negative, again direction would have been like this. If it's positive and negative, this direction will be towards and this direction also will be towards. But we found out that the magnitude is equal. The same way we can calculate acceleration also. This acceleration and this acceleration. Acceleration may be different. Why? Because masses can be different. This is m2 and this is m1. So acceleration will be different because of the masses, but the force on both is equal and opposite. When the forces are equal and opposite, and both these particles are applying the force on each other, then we can say these forces are what? Action, reaction. Action, reaction forces, or they are making action, reaction pair. Okay, they are making what? Action, reaction pair. Is that clear? So, if suppose on this property itself, that the electrostatic force is action, reaction pair, I give you one question. Can you solve that? Let's see the question then. Okay, so there is, let's say, here is charge 2 coulomb and here is charge 4 coulomb. Its mass is 1 kg and its mass is 2 kg. Okay, its acceleration is 2 meter per second square. What is its acceleration? Okay, the motion is because of electrostatic force between them. Motion is only due to electrostatic force. Find acceleration of 2 kg mass. Okay, what is the acceleration of this? How to find? Very simple. We know that electrostatic force is only responsible for their motion, and electrostatic force is action, reaction force. That means the force acting on this object will be same as force acting on this object, right? Force on this due to this charge and force on this due to this charge is equal and opposite. So how much is force on this one? Check. If I say this is charge number 1, so force on 1 is equal to mass into acceleration, 1 into 2. So force on this also should be what? 2. Same. So F2 is also 2 Newton, which will be equal to its mass into its acceleration. That means 2 into 8. So acceleration is 1 meter per second square. Very simple. Okay. In the same question, if I change, I make it a momentum question. Let's see how you do that. If I say that this object at any moment is moving with the speed of 20 meter per second, then what is the velocity of this one? What is the speed of this one? Okay, how to do this one now? Exactly same way. Why? Because we know that the force acting on this, okay, let's say that's F2, and force acting on this is F1. But we know that their magnitude is equal. Magnitude of F1 is equal to magnitude of F2. And if I am going to add them, so the net force on the system will be F1 plus F2. And I know that it will be 0. Why? Because the directions are opposite. So if net force on the system is 0, we can conserve momentum. We can conserve momentum. If F net is 0, then momentum of the system is conserved. Momentum of system is conserved. So what is the initial momentum here in the system? 0. Because after the force started acting, then only they started moving. But initially, what was the momentum? Momentum was 0. So initial momentum 0. Final momentum? Momentum of this plus momentum of this. The momentum of this, it's in towards negative direction, towards left. So I'm taking it negative. So let's see, that is m into v, 1 into 20. 1 into 20 into minus I cap. Here, 2 into v. Okay, then we know that initial and final is equal. So here also I am going to make 0. So this is minus 20 I cap plus 2v cap. What are we going to get? We are going to get v is 10. V will be 10 over here. Is that clear? So from the first observation itself, from the forces, we have solved few questions. So what property we got? We got that electrostatic force is an action-reaction pair. Force applied by one charge on the second and second charge on the first is equal and opposite. Okay, now if the charge is Q1 here and the charge is Q2 here. Okay, let's assume that force applied by Q2 on Q1 is in this direction and Q1 on Q2 is in this direction. Are we talking about these are action-reaction forces? Are these action-reaction forces? Answer is no. The action-reaction forces that we are talking must be on the line joining two charges. Action-reaction forces must act along the line joining two charges. Okay, the forces shown here are not on the line joining two charges. So these I cannot say action-reaction forces. Action-reaction forces has to be like this. Okay, and because of these reasons, these forces are also called as central forces. Okay, what are central forces? When the force is applied by one object on the other object is along the line joining two charges or two objects, then the forces are called central forces. Okay, same word was normal contact force. If you remember momentum and collision, in that chapter you studied the central force. Okay, so normal contact force is also a central force only. So these are the properties. This is first property. Second property that we are going to discuss about the forces is electrostatic force is a conservative force. Third property, electrostatic force is a conservative force. What is the meaning of conservative? Conservative force meaning is work done by these forces does not depend on the path. It only depends on initial and final positions. Work done by conservative forces only depends on initial position and final position of the path, and they do not depend on what kind of path is being traveled. Okay. Second more important thing is for conservative forces, work done by them is stored in the form of potential energy. Okay. Work done by them is stored in the form of potential energy. That is how the electrostatic forces are. And before this, what we have studied as electrostatic, or rather conservative forces, gravitation force, magnetic force, and spring forces we have studied as conservative forces. Okay, so this is one of the property of electrostatic force. Fourth property, if suppose we have a charge Q1 over here and a charge Q2 over here. Okay, we know that there is a force on charge 1 due to 2, and here is force due to charge 1 on 2, and this is force on charge 2 due to 1. It's like this. Now suppose another charge Q3 is brought over here. So what will happen? This will be subjected to another force which will be in this direction. Force on charge 1 due to third charge. This will also be subjected to a force which will be like this. Force on charge 2 due to 3. Okay, but the force due to Q1 on Q2 and Q2 on Q1 will remain same. Again I am saying the net force on Q1 definitely has changed because of the presence of Q3. Net force on Q2 definitely has changed because of the presence of Q3. But force applied by Q2 on Q1 or Q1 on Q2 remains same. Okay, it's very important property. The force applied by one charge on the second charge is independent of the presence of third charge. Okay, force by one charge on the second is independent of the presence of third charge. Of the presence of third charge. Okay? Let's see further. So let's talk about the force between two charges again. There is charge Q1 here, there is charge Q2. Okay. When the forces were measured, okay, it was experienced that the force between two charges, we know that force on Q1 due to Q2 and on Q2 due to Q1 is equal. We know that. And it's opposite. But that force magnitude is directly proportional to the product of magnitude of two charges. Okay, it's directly proportional to the product of magnitude of two charges. That means if this charge is increased, force increases. If this charge is increased, force increases. If you are decreasing those charges, force also is getting decreased. Another factor that was checked was the separation between them. When the separation was varied, this force also started varying. So it was observed that this force is inversely proportional to R square. Okay? So when you combine them, it is written as F is directly proportional to Q1, Q2 by R square. This proportionality has to be removed. So one constant is brought. 1 by 4 pi epsilon naught. Q1, Q2 by R square. Okay. Now this is the force on Q1 also. This is the force on Q2 also. Remember that. Equal and opposite. So this 1 by 4 pi epsilon naught. In this one, this is called permittivity. Permittivity of free space. Or vacuum you can say. And it has got a value 8.85 into 10 to the power minus 12 coulomb square per Newton meter square. Okay, what is the meaning of this permittivity? It is the property of the medium. It is a property of medium due to which it allows the electric field to pass through it. Okay, electric field can pass through a medium because of this property only. So does it mean that it is having different value for different medium? Yes. This is 8.85 into 10 to the power minus 12 is for vacuum, or you can say for air. Okay, for a conducting body, the value of this epsilon naught is infinite. Okay, its value will become infinity. Alright. And if suppose this 1 by 4 pi epsilon naught, if we are going to keep its value in free space, this can also be written as 9 into 10 to the power 9. 1 by 4 pi epsilon naught value is 9 into 10 to the power 9. But again, it's in free space. When you are going to keep epsilon naught is 8.85 into 10 to the power minus 12. Is that okay? And the unit of the force is Newton. Okay, so that's all for now.